Okay, welcome, and this is Chipmaster, and in this video series I'll be working on a laptop, a HP laptop that's turning on and off. Right, so I got it from a technician and it said that it was liquid spilled, and after he cleaned up all the liquid and stuff, it's still turned on and off. So he took it to me to repair. I got it from him as is without the back. Right, so this is it, and he said that he tried everything, cleaning it up as best as he could, but still turning on and then off. So I'm gonna see what's going on now. I'll plug it in the power. Do I have the power? Alright, so okay, the battery is charging. I get the orange light, as you can see. It's charging. Alright, battery is charging, and it's taking some ampere there, indicating that it's actually charging. It's 1.6 amp. So I press the switch. This is the power LED is on this side, so I'm gonna press it. Oh, there it goes, and it goes off, as you can see. Let me press it again. Right, the light comes and it goes away. There we go, see? So it's not staying on. And I'm pressing it repeatedly, and it can be repeatedly triggered. Normally, if in a power failure issue like this, if you press the switch and you have to remove the battery and the adapter and press again and it does the same thing, that means that's a short on the rear stage on the secondary supply. But if I can continually, repeatedly pressing the switch and triggering the board, that indicates a power protection problem on the motherboard. So it's not a short circuit in terms of that it's a short on the rear stage that is causing it to power down. Right? So as I'm pressing the switch, it keeps powering off, not staying on. Alright, so I'm going to take it apart and see what's going on. Alright. Zoom out a bit. Right there, I think. No? Yeah. That it should be fine. Trying to get the wires out of the way. Oh, I did it wrong. These laptops are very popular in my country here. Alright, yeah, I call them the budget laptops. What most people here can afford. These HPs are a bit cheap. There are a lot of them here. A whole lot. I repair these like every week, sometimes 3 times a week. That's the amount that's actually here in this country. So I call them the budget laptops. So they purchase them on a budget because they're cheap. HPs on a whole these HPs on a whole are budget laptops in my country. very low end computers. These are 11th gen CPUs rather. I believe this is a Core i5, I believe. Yeah, or i3. It's a Core i3 there. Alright, here's some watermark here. Oh, here's some watermark here as well. We didn't clean this side. We didn't clean this side, as you can see. This side was not cleaned. So that's liquid. Let me clean it. So you can definitely see that's water because it's white when dry. So that's definitely water there. Alright, so I can see that he already cleaned some parts of the board water. Oh, he didn't see this side. Probably just cleaned the surface only. This side. Alright, so he cleaned it. So it said he cleaned it. I'm looking. Let's see if I see any more liquid corrosion. Alright, that side is good. Alright, this side needs a little more cleaning here. Alright, that's cleaned. Where else again? Where else is in the CPU area? I'm looking. Don't see any liquid on this side. It's mostly on this side that he was cleaning. Oh, here's some more here, right at the edge here. And that's now cleaned. Let's look under the RAM. Checking the RAM. All clean so far. Looking good. Next one. Looking good also. Looking good, looking good. Aha, here's some more. As you can see, some more liquid here. Alright. Checking into the RAM slot now. Looking into the RAM slot. Where is it? Alright, the RAM slot. The RAM slot looks good. Next one. Alright, the RAM slot looking nice. No liquid inside the RAM slots. Checking again at the back. Oh, this part is good. Looking good. Alright, so checking down inside of the HDMI connection there. The Type-C connection there, looking good. Looking good. Alright, so I'm gonna plug the power. So I'm gonna take out the DC jack. I think I have a DC jack already. I don't have to take out the one on the laptop. Alright, DC jack is in. Okay, I'm gonna connect the switch. Let me connect the power switch. There we go. Alright, so I'm gonna press the switch again. You can see the light is there and immediately off. Light is there, immediately off. Alright, so I'm going to use the oscilloscope now because of how the power failure is so fast, the multimeter will not be able to keep up with this power failure. So the only way you can capture if the voltage is coming out is using the oscilloscope. Alright, so I'm going to go over to the picture. Alright, so we're at the oscilloscope now. Alright, so I need to turn down the aperture. So you can see the waveform. Alright. So I'm just making sure that my settings is okay. Okay, that's good. Trigger level. Alright, and my volts per division is 2 volts per division. So as I press the switch, I'm going to check each power rail and the coils to see if the voltages are produced properly. Alright, so first this is 3.3 volts, and before these voltages are not generated immediately as you plug in the adapter. Right, so on this board the voltage is only going to be present after pressing the switch. So right now I'm having my probe here on 3.3 volt output filter capacitor pad. So incoming voltages or signal coming into my DC on my oscilloscope. So I'm going to press the switch. As you can see, very good, there I have a rising edge and it falls quickly because of the power failure, and that's 3.3 volts. So if I set this to my single trigger, if I set the oscilloscope here to the single trigger setting, we can now capture the signal and then we can analyze it. Okay? Ready. I'm pressing the switch now. Oops. Let me. Alright. Alright, so I'm going to press the switch. I think I need more time. 10 volts milliseconds. Let me see. There we go. So as you can see, this is 2 volts per division. So that's 2, 4, and in between that's 3.3 volts. Right, so 2, 4, and in between, so that's 3.3 volts. So that's good. So let me clear the screen. Let's check 5 volt now. 5 volt is right here. Oh, I'm having an interference here in my probe. Alright. It's capturing something here. Oh, I see. My trigger level was too low. Let's go. As you can see, I got a waveform, so that's 2, 4, 5 volts. So 5 volts is also okay. Okay, that's very good. Now, for the 11th generation, we need a set of working conditions in order for the CPU to initialize and to start the ACPI configuration. Right? And that is RTC reset, SRTC reset. At the moment, there's no schematic for these models because I repaired them so many times. I can't find a schematic nor a board view to repair these devices to a certain extent. So I use my experience, and I know most of the chips working conditions on this board. Pretty basic, right? So there's no schematic and there's no board view. As you can see, the board view, the board number here, Right, it's DAOP5HMB88J0 revision J, right, and there's no schematic for this model or board view, so you have to have some form of experience to repair this board without a schematic. Let's zoom in some more. Alright, so I have RAM supply and I have VCC PRIM 1.8 RSM reset, and we have the power switch which is coming from my actual power button. Now this side here is 1.8 volt rail, so I'm going to check the 1.8 volt rail. Let's clear the screen on the oscilloscope. Let's see if we get 1.8 volts. No 1.8 volts. We got 1.8 volts. As you can see, we got 1.8 volts. So this is 1 volts per division. So I set my time base, my voltage now to 1 volts per division. So this is 1, 2, and as you can see, it's all the way up to close to the 2 grid. So that's 1.8 volts, perfect. Now, the next thing now we need to check if the RAM, if the CPU actually release ACPI configuration. So 3.3 volts is okay, 5 volts is okay. Let's check if we're getting RTC clock first, VCC RTC. So I'm going to set this now to 500 millivolts, and my trigger level is going to set to 500 millivolts as well, and I'm going to set my time base to 100 microseconds, and my edge type is set to rising edge. Take a look. So this is the crystal, 32.768 kilohertz. So I'm going to take this from, we're actually capturing something now. I captured this clock, so the clock is working. There we go. So as you can see, I have 30. I don't know if the camera can pick it up. So I have 35 kilohertz. Let's try again. There we go. 32.2 kilohertz, 31.3 kilohertz, 33 kilohertz. So it's working. You can see the wave. So I'm getting wave there, as you can see. Alright, so next I'm going to check if we are getting RAM supply. This is the RAM supply coil here. Let's go. So I'm going to set back my trigger level, my volts per division to 2 volts per division, and my time base is going to set to 1 millisecond, and my trigger level is going to set to 1.1 volt. Alright, this is a DDR4, so we should get 1.2 volts. Right? So I'm setting this to 1 volts per division for clarity and demonstration. Right? I'm not getting anything. Not getting it. I'm pressing the switch repeatedly, and there's no waveform coming in. It's not capturing anything. So first of all, we need to locate this chip part number. So this chip, I'll have to go under the oscilloscope, under the microscope, sorry, to see the part number of this chip. Let me turn off this part. Alright, so under the microscope we have, let me pause. Alright, so I'm under the microscope now. Alright, so looking at the chip now here, as you can see, the part number or the code number, this is a Rich Tech chip. And it's 3TAB. Right, so the chip is 3TAB. Right, so this chip, I believe, is a RT8231, I believe. Alright, so I'm gonna go on the web. Okay, so So I found the data sheet. Remember, there's no schematic for this board, so we'll have to use data sheets and experience when repairing these laptops. There's no schematic nor a board viewer. Alright, so this is it. This is the chip. That is the RT8231. We have A and we have B. Right? And remember, this chip starts with 3T, right? So the code number, see, we have 3TYN, and on the board that I have here, it begins with 3T, right? And that's the code, as you can see here, the date code, and we start with the product code, which is 3T. Anything after that is the actual day and the actual current date of manufacturing, which is not really important. What is important is this part. So we have 24 and we have 3T. So 24 is RT82, right? So let me zoom in some more. Right, so 24 is RT8231A and 3T is RT8231B. Right, so this is the difference between them. Right, and they give you the A and the B. So the A has tracing mode, right? The B has non-tracking mode, right? And this is some features of it. It's an adjustable current limit with low side, which is resistance from drain to source, sensing the ground MOSFET, the lower MOSFET, which is connected to the ground, right? And it has a quick load step response with 100 nanoseconds, and the different family or generation rather of RAM. So you have second generation, third generation, third low voltage or low power generation, 1.2 volts, and LPDDR3 and DDR4 fourth generation. So this chip support all these generations of DDR RAMs, right? So the input between 4.5 to 26 volts, right? And it has a resistor for adjustable frequency and for over and under voltage protection. But for in our case now, we need to check the pin out, such as the enable pin, the supply enable, and the output, right? So as you can see, here is the block diagram or our simplified application. And this is the pin out that we actually need. So we have the top view. So this is the first pin that we need to check is the power, which is pin number 5. Sorry, VDD, pin number 12. Right, next we have S3 and we have S5. So S5 is for SLPS4, which is an ACPI control signal, which stands for Advanced Configuration and Power Interface, right? And this is used to put the computer into different states, such as S4, S3, S5, right? So that's ACPI, and that is controlled by the CPU, right? Because it was developed by Intel and Toshiba, right? So Intel implemented this to put the computer into different state in order to conserve or to consume power, or for power consumption. So you don't have to have your computer running all the time and burning out the components and shortening the lifespan of the components. So they come together to develop the ACPI, which is called Advanced Configuration and Power Interface, and that is where it is coming from. This from the CPU, which is used to control SLPS3, and this is SLPS4. Right, so for the AMD, for the Ryzen, all AMD CPU from the Cabinis, the Hudsons, all of them use SLPS5 instead of SLPS4. But for the Intel series-based CPU, it uses SLPS4. So don't watch this. This is SLPS4, and this is SLPS3. So this is turn on the RAM supply, and this is to turn on the VDDQ, which is here, and the voltage reference, and we have our VTT, which is a RAM termination supply, and this is a LDO. So this side, all of this side here is LDO, and all of this side here, from here, you have up, gate, phase. This is the PWM section, right? Let me get my pointer fix. Okay, so as I was saying before, so this side is from here, where you have boot, up gate, phase, lower gate, power ground. This is the PWM section, right? So it's PWM, that stands for pulse width modulation. And then all of this side here, from here to here, is the LDO section. So that's LDO, that stands for low drop out. So this voltage coming out of here is 0.6 volts, which is half of the main voltage, as we all know, right? Because the main voltage of a DDR4 or fourth generation memory is 1.2 volts, right? So 1.2 volts, right, divided by 2, which is going to give you 0.6 volts, which is half of the 12, half of the 1.2 volts, sorry. So this part is the LDO section, and this part is the PWM section. So what we need to check first now, we need to check the enable, the main power supply, right? So this is the power, VDD pin number 12. Then we need to check SLP S4, sorry, which is coming to pin number 8. All right, let me fix that. All right, so we need to check here, pin number 8. And as I said before, we need to check the power first, 5 volts. So once 5 volts is coming, and we have 3.3 volts here, that indicates that the CPU is okay, so it's releasing or sending the ACPI configuration. But so if there's no output on the PWM section here, then you need to check the rear stage if there's a short on the rear stage of the coil. And then we need to check the upper MOSFET, the lower MOSFET gate PWM waveform, the upper MOSFET gate waveform. If all the waveforms are intact and still no output, then you should change this chip. And if you get what I'm trying to say right here. So this is the working order and the process in which you should check a typical PWM IC. So first you check the supply, then 3.3 volts, then upper gate waveform, lower gate waveform, then you check the rear stage of the coil for the waveform. If there's no waveform, then you replace this strip. That dead simple. Okay, so let me go over to the microscope. Sorry about that. Let's go to the microscope. Okay. Alright, so as you can see, hold on, sorry. Alright, so as you can see, remember we have 3T. So it's 3T AB, so this is a RT82 31B, right? RT82 31B series. So first of all, we need to check pin number 12. Go back to the chain, to the oscilloscope. So I'm gonna check pin number 12. Pin number 12. Let's go. So this is pin number 1 mark. Alright, that's 1. So let me just align this properly. Yeah, there we go. That's pin number 1. 1, 2, 3. Focus is not clear. Okay, good. That's 1, 2, 3, 4, 5. And that's 10, 11, and 12. Here's a capacitor for it. So I'm gonna connect the power now. Oops, sorry. Alright. Pin number 5. Pin number 12, sorry. The wires are in my way. Did I hear something? Oh. So I'm gonna press the switch. Oops, yes, we got it. Hold on, let me set my volts per division to 2 volts per division. Alright, number 5. Pin number 12, sorry. So we get 5 volts. So 5 volts is there. Alright, next we need to check the enable pin. And the enable pin, which is pin number 8. So that's 1, 2, 3, 4, 5, 6, 7, 8. And it's coming to here. So let's check if we're getting 3.3 volts there or not. Yes, we're getting 3.3 volts. As you can see, we are getting the enable. SLPS4 is releasing from the CPU. So the CPU working conditions is okay. Alright, let me clear the screen again. Let's check again. I'm pressing the switch. Right, there we go. We get 3.3 volts. Let me clear the switch one more time. Clear the screen. Right, this is the point. We're going to check here. SLPS 4. Yes, and we get the voltage there. So it's 3 volts right there. 3.3 volts. Let's check the back end of the coil now. Of the RAM supply coil. Back end. This is the back end of the coil. And let's check if we're getting voltage coming out. No voltage coming out. Let me clear the screen first. Pressing the switch. No voltage coming out. So that means our chip is bad. Remember I told you how to check the working conditions. Check the supply and the enable. If there is no voltage coming out, then you should replace the chip. So we're going to replace the RAM supply chip and see what we get. First of all, let's check the resistance to ground first. I didn't check the resistance, did I? No, I didn't check the resistance. I just inspected it with my eyes for liquid corrosion. So I forgot that step. So I'm going over to the multimeter now. Just increase the aperture on this thing. Alright, there we go. So what is the resistance on the RAM supply coil? I don't know. I'm gonna check it now. Alright, red probe on ground, black probe on the coil. And I get 42. That's a little bit too low because the RAM is out. That is too low. I should be getting a roughly 200 or 180. And I'm only getting 42. Alright, if this is a short here, the CPU is dead. If there's a short, the CPU is 100% dead because the CPU has the memory controller inside of the CPU, and the CPU memory controller needs this 1.2 volts. It is shared between the RAM and also the CPU, the memory controller inside of the CPU. Right, so if that signal is not coming out, if that is shorted, then the CPU is dead also. Now this chip here is a low dropout voltage chip. This is going to send 2.5 volts to the pin here on the RAM slot, this pin here. So 2.5 volts should be coming here. So that is controlled by SLPS4 also. So let's see if that's coming out of the chip as well. 2.5 volts. Alright, so I'm lowering down the aperture again. Let's check if we're getting 2.5 volts there. Done. Alright, so we're going to the memory slot now. For 2.5 volts, is there or not? Oh, I think I'm on the wrong place. Sorry. It's the wrong side. That's the wrong side. Sorry, that was my mistake. It's here. I was at the wrong point there. Sorry. Here is a 2.5 volts. Right here. Okay. Press the switch. Yes, we get 2.5 volts. As you can see, we get 2.5 volts, and the machine is powering off, so it's going back down. See, 2.5 volts. Alright, so if I put this on back to the single trigger, alright, set this back to single. I want to keep the volt, I want to keep it so it don't move, so I can analyze. Let's go again. Press the switch. Yes, and we get 2.5 volts, and that's 1 volt per division here. Sorry, 2 volts. This is 1 volt, this is 1 volt per division also. 1, 2, in the middle of 3, it's 2.5. So that's good. So, but we're not getting our voltage here. So first I'm going to remove the the RAM supply chip. I'm going to disconnect this side of the coil first and see if the tension is on the rear stage or on the front, on the back end or the front end of the coil. Alright, so waiting for the iron to get hot. Here. Alright, so I'm just adding some low melt solder here so I can free up this coil and lift. There we go. So I lift it. Right there. Alright, so I'm going to check the resistance now. So I'm going to check this side. And I get 484. And I check this side and I get 42. So the CPU power supply, sorry, the RAM supply chip is pretty good. The RAM supply chip is good. Alright, so whenever you see this, then you know there's a problem on the rear stage. Then you know that the CPU most likely got a hit, but it's pretty high though. Well, before I didn't get an over voltage or a protection to indicate that the chip actually releases the voltage. So the oscilloscope actually told me that there's no voltage coming out, so that means the chip most likely could be bad because it's not outputting any voltage, any at all. If it was outputting voltage, then it shuts down, then I will say the chip is good. So there's a problem on the rear end. Could be an over voltage protection problem, or under voltage or over current protection. Alright, so I'm checking it directly under the CPU, and I'm checking under the CPU here, under the RAM slot here. As you can see, I have some cleaned up area here that was cleaned by me and the other tech. And if I measure any of these capacitors here, it should give me the same reading, 43. Alright, any of these 20. That's ground, yeah. 396. .43, here it is, very good. Alright, so 43, 43, 43. All of these cap. See? I get back to 43. Measure here. I got back 43. There's one more here. 43. They look alright, and they are not cracked. I'm going to just remove the RAM supply chip first. And measure again. Yeah. There we go. Alright, here again. It's 27. I'll let the board cool a little bit. I'm gonna lift one of these caps and see if these caps are okay. These filter capacitor to ground here, and I get 26. The resistance is even lower than before. Interesting. Alright, so this side I'm getting 435. I'm waiting the board to cool because the board is hot, so it's still gonna give me 43 because the board is hot, so it's giving me a lower value. As you can see, it's increasing. So it's not increasing the way I want it, so it's not the chip. So I just wanted to confirm and make sure that the chip is good. I'm going to lift this cap first. I'm going to lift one of these cap and then see one at a time. So it's slowly going back to 43, so now 33. Let me see if I can peel off this plastic. Alright, so here it is, 34. Not good. Alright, so I'm going to lift this capacitor first. And then see what I get. I think I'm just going to remove. I have to remove them one because if I remove the two of them and the tension is cleared, then I would not be able to know exactly which one is the culprit. Yeah. So I'll just lift this one. Alright, so I'm just need some more solder here. There we go. And I'll measure now. Still same, so it's not it. Next one. Kind of a bit difficult to remove on this angle. I'll just use hot air. Oh, there we go. Came off completely. Yeah, just let it see if I see any difference. Still the same. Alright, so I'm gonna put back a different chip here. I'm gonna put a new chip on this pad here for the RAM supply, and then see what I get first. Tinning the pads. It's gonna take one from a donor board. I have them new, but they're in a drawer and I can't bother to go and search for those new chips. So I'll just take one from a donor board, quick and fast, easy. Alright. Let's take out this excess here. Just take this one off from this board. This is a donor board. Oh. Bring the excess solder here and here and here and all right. Clean. Oh shoot. Coil. I know solder back the coil. Alright, and I'll just put back these capacitors. Filter capacitors here. And these are 0603 capacitors. Right. Oh. Oh, I don't see why. That's one. Take this one from another board. Oh, that blew away the second one. All right. $33. Actually, even lower than I think. All right. Connecting up power supply now. Alright, pressing the switch, and it's the same thing, no voltage coming out. Alright, so I believe the CPU may be dead. The CPU maybe died. CPU may have died. These boards, the CPU are easily broken. These CPU, these 11th generation CPU, they die very easily. Slightest of liquid or any spike, boom, the CPU died. Alright, so oh shoot, what did I end up with these? This board needs cleaning. Oh shit. Sorry. Okay, so now I've removed the coil. Checking the capacitors. These capacitors here, yeah man. Yeah, these caps here. I'm just gonna move them one by one again. Alright, that one is removed. And we're gonna check again. Increase the aperture here. Check here, still 39. Alright, still 39. Let me remove the other one. Alright. Still 40, 39. So it's not the capacitors, because the resistance here should be roughly 100, 150 ohms, and I'm not getting it. And I already checked these capacitors already. All main filter capacitors are checked, and that's indicating that the CPU had died. The CPU having the problem. 39. Let me see what the resistance is if the CPU is installed. CPU is installed, and I get 27. I get 27. Check under the okay, so I had to pause the video because the video would be too long, and I did some thorough visual inspection, and I see here we have a scraping a via right here, and this is taking a voltage or a signal from this side of the board to another side of the board going into the board. So as you can see here, it's rusting, and the trace is basically broken, as you can see right here. Right, so after doing some visual inspection, because I was saying that I'm getting 43 and that's reasonable, so I compare the resistance on the memory supply to another board, and I got 68. So I'm saying, that means the CPU is not dead, because I'm getting 43. That's not fully dead. That indicate that there is a problem maybe inside of the board. After checking, and as I said, I was thoroughly checking every single layer under the trace on the other side of the board. I see that check all these traces here. As you can see, I was tracing them and making sure that they are not broken, and lo and behold, I found this. And this is I'm not sure what this controls, right? Because I'm not sure what, but it's very thick, so it indicates it could be a ground pad. It also could be a power line, and it's broken, as you can see here. So what I have to do is I have to get the other board, and by looking, it's very close to the RAM supply. It's basically directly under the RAM supply section there, right? So under the RAM supply chip there, I can see that section there is right under the RAM supply chip. Trying to get this there. Almost directly. So I'm just marking right under it, directly under the chip. And this is the only damage I've seen so far on the board due to layers. So I'm going to power the board and see how much voltages is this, or if it's a ground pad. Let me check if it's a ground pad first. Let's scrape in this part here. Alright, let's check in if it's actually ground. No, it's not going. 457. 457. That seems like 19 volts. I'm going to check if it's 20 volts going through this line. So I'm going to connect the power now. Set this to voltage. Oh, it's 20 volts going there. Okay, and I know this is broken because it's not coming through. So I will see if I can use some solder paste and then scrape here and see if I can get that connection back. It's not going to be so easy, but you can see it's actually 20 volts there, and you can see here it's broken. There is no trace here. All right, let me zoom in to closer. As you can see, a piece of it here is gone. This is just the material of the board. There's no copper trace here. It stops right here, and here's a copper trace here, and I'm getting 20 volts. So I'm gonna see if I can catch back this lead. It's not gonna be easy, so I'll have to scrape with my blade to see if I can get into the via so I can jump a wire with the help of solder paste. I'm not sure where is this going, but it's going directly under the RAM chip, but the RAM chip doesn't need 20 volts. But I know this is a disconnection here, and that can cause some serious problems. Alright, so I'm just trying to scrape into the via here so I can hopefully use solder paste to make a joint. As I said before, I don't think it's gonna be easy. Or what I can do is just run a wire from one side of the board or another side of the board and send 20 volts there, and hopefully, no, but this is going into the board, so I can't, because this is 20 volts on this side of the board. It needs to go to the next side of the board, so that won't work. And I'm not sure which point this is, unless I have to get a working board, another board, and see if I can you know what, let me get another board. This is the same board. I have another board here. And this is the via that we are looking at. This is a board. This is also dead. This is not a working board. This is a donor board. Alright, this is a donor board. Oh, here is it. This is where we're at. Okay, so I will solder a wire here, and then I will use my meter and see where I get continuity on the next side, and then now I can just run a straight wire from there to the target area. So I'll have to solder a wire here and wrap my leads around this. So I'm just going to wrap my leads around this. I'm just going to solder us right there, and then now I'm going to use the meter probes in the continuity to see where on the other side of the board this is connecting. Alright, I hope I don't tear this out. You know what, it's better for me to put this at a different part of the board. I don't want to tear out this lead, so I'm just going to scrape here. Scraping it, expose the copper so I can solder the wire better here. I don't want to solder it directly in the joint there, and if I make a mistake and and something happen, it's gonna rip out the entire via, and then I can't be able to locate on the other side of the board where this trace is connected. Just exposing the wire here. I'm gonna solder it parallel as parallel as I can to the, oh yeah, this way, so I don't tear out anything. Alright, there we go. So I have a good joint there. So I'm going to wrap one of my leads now. Okay. Alright, so I'm just gonna wrap the wire around here. As I said before, there's no schematic, so this is making my repair a bit harder. Alright, so that's one there. See if I get, not getting any beeps. Hold on. Oh, see, I have ripped out the thing. I was trying to, oh, let me pause. Okay, so I've taped it now, so I don't want this wire shift, because if it's wire shift, my repair is dead. So I won't be able to repair. If I make this wire shift and break this via, then that's the end of the repair. So now I've just made a little circle here, so I just put the probe here, any probe, it doesn't matter, so I don't have to worry now if this moves or shifts. The tape is there to hold it. Right, so as you can see, this is a donor board. I removed the CPU, right, and some other chips, so I've taken off most of the parts of some of the parts from this board. Right, so I'm on the side of the board now, so I'm going to check each pin of the CPU of the RAM supply chip, and if I get a beep, then that's where I'm gonna that's my location of the fault. So I will switch over to the microscope now. So I'm targeting my focus in the RAM supply area, because I'm not getting the RAM supply. I'm getting the power supply, I'm getting the enable signal, but it's not outputting. So I'm gonna check here. Oops, I took up the wrong probe. Sorry. See, I could have torn the via again. Alright, so I'm just checking along here, and if I get a beep, then that's where my fault location is. Checking every capacitor, every resistor. Alright, nothing there. No beeps. No beeps. Aha! And I'm getting a beep here. I'm getting a beep here. And this is a resistor going to this pin. So I wonder if it's a soft start selection pin or the turn pin, time on, which is the time on pin, to tell us the MOSFET how much frequency these MOSFETs should be switching at. Right? So this could be the turn pin, because normally a turn pin connects to the 19 volt bus to 19 volts, and then it is passed through a 300 or 400 kilo ohm resistor, and then it is sent to the pin of the RAM supply chip. So this is what pin, let me check, 1 2 3 4 5 6 7 8 9. So let's go to the data sheet and see what pin number 9 is. Okay, pin number 9. So I'm correct, it's the turn pin, which is pin number 9. So this is the frequency selection pin to tell the MOSFET at what frequency should they switch at and how fast. So let's go to the documentation for the pin. Let me zoom out. So let's look for TON. So see, it set the upper gate on time through a pull-up resistor connecting to VIN, and that is 19 volts, right, or 20 volts. So this is the fault that I'm experiencing now. So I'm not getting the turn pin. So the RAM power supply chip doesn't know how much frequency to control the upper gate MOSFET in order for it to switch the output voltage from 19 volts and breaking it down to 1.2 volts. So it's not going to output anything, right? So this is done through the TON, which is the time on, or the on time, how long this duty cycle should switch for. So the duty cycle is basically used to calibrate or to measure the amount of voltage and how long that voltage should be generated for before closing. So a typical pulse width modulation circuit goes on, off, on, off, on, off. So that on pin, the TON, is it on, so it's on, stop, on, stop, on, stop, on, stop, on, stop. So the on, which is the on time, tells the gate how fast and how long it should switch for. And it also set the frequency selection for the PWM output. I wonder if you get what I'm trying to say right here. So this is done through the turn pin, which is pin number 9, and it is this pin, TON. Alright, so So that's it. So what I will do now, I'll just run a wire. So this is a donor board. So let me get my working board, the board that I'm working on, sorry. So I have missed the on pin, and here is the resistor here. Here is it. So what I can do is just take 20 volts from here and just run a wire to here. Alright, so this is 20 volts. This is the upper MOSFET gate. So this MOSFET is what is controlled by this resistor here for the on time. And I will just run a wire from here. Right, this is 20 volts from here to here. Alright, so let's go back to let me get the multimeter. Okay. Alright, so let's go back to the voltage gear. So I'm gonna plug in the power now. Alright. So here I should get 20 volts. I was supposed to be getting 20 volts. I was supposed to be getting 20 volts here, but I'm not getting it, as you can see. Right, so I'm getting 20 volts here at this capacitor here. Right, these are, so I should be getting 20 volts here. As you can see, I'm getting the 20.46 volts. So I'm just going to take the 20 volts from here and send it to here and see what I get. Alright, so I'm just going to use the insulated wire here for the jumper wire. Since it's just 20 volts, I can take 20 volts from basically anywhere from this thing. And that's V in pin according to the data sheet. So I'm just going to connect the 20 volts on this side. That's a bridge there. Alright, here we go. I have another board like this to repair. I got two of them at the same time from the same tech. So I will do that one off camera because I have a lot of work. Let me add some more flux here. One right here. Alright, so I'll just run that wire here. The 19 volts comes to this part of the resistor here, right here. So I'll just put that right, just expose this part here. And solder it right there. Right here. There we go. There we go. Alright, so I'm just going to cut that right here. There we go. So I'm just going to let this come between here and here, so I don't have to worry because it's insulated. And I'm gonna power the unit up. Let me see if I soldered the wire. Oh no, I've soldered it to the wrong capacitor. That's ground capacitor. What the hell? Ah, God. It's supposed to be soldered here, not here. It's supposed to be soldered right here. I have it. Alright, right here, right here, right here, right here. right there. And good. Alright, so I'm gonna give power now, and let's go back to the oscilloscope and see if we're getting voltage now. We're getting some voltage now. Let me zoom on. So I'm gonna turn down the aperture now. Alright, turning down the aperture. There we go. Okay. So let me just setting up back the camera right here. Picture. Alright, so I'm gonna connect the power oscilloscope. So let me set back my volts so everything is intact. Rising edge. Alright, and let me see, should get some voltage here or not. Yes. Let me set this to single trigger. The board is turning on. I get resistance. Everything is outputting normal. Single trigger. Alright. Rising edge. Take a look at the screen of the oscilloscope to see RAM supply is there. Alright, so I give power. Oops. Set my time base 5 milliseconds. Ready. There we go. 1.2 volts is there, as you can see. Now 1.2 volts is now outputting, and the laptop, the motherboard has been powered up. So I'm going to put this together. First of all, I'm going to see if I can check all voltages coming out properly. 1 millisecond, and I'm setting this to, oops, normal. Alright, here we go again. Alright, so we start off with the other one. No more on this one. Okay, sorry about that. It's working time now, so the workers are actually coming to work now. Alright, so about 3.3 volts. I was checking all the rails now, making sure they are all generated properly and outputting. Alright, 3.3, let's go. Oh, my heatsink. Where is it? Oh, give power. Good, so I got 3.3 volts. That's good. 1 volts per division is needed. Next, we have 5 volts. Give power. Give power again. There we go, we have 5 volts. Next, 1.8 volts. VCC PRIM 1.8. I give power. There we go. 1.8 volts is outputting. Next, we have VCC. This is 1.8 volts again for the VCC in AUX supply for the 11th and 12th generation Alder and Tiger Lake. Very good. 1.8 volts is outputting. We have CPU core. I give power. Next. Excellent. VCC core, CPU core is generated. Alright, the graphics. This one is going to come, I think, after, I believe, after passing the memory. Okay, we have output. Alright, let's see if the CPU is actually reading the memory. So this is going to go to a falling edge. There we go. So we have pin number 4. All I can't see. Let me just go under the microscope for a second here. 1, 2, 3, 4. Let's see if the CPU is reading memory. Alright, I give power. Press the switch. Don't think I'm on the correct pin. Let's go back on the microscope for a minute. Alright, so I'm giving power now. There we go. So the CPU is reading memory. Alright, there we go. So everything is passed. So we'll just put this thing together now and see what I get. This was a tough repair because I didn't have a schematic. Alright, so putting back on the heatsink. The RAMs. Alright, somebody just texted me a while ago that they have a laptop that goes dead on them a while ago. I just told them that I'm full, can't take any more work, and he's saying that it's urgent. And I have somebody coming here with another one, which is another urgent one. It's a technician, rather. Okay. Oh, sorry. Okay, so now I'm going to test. Right, that was a very long repair. Right, and because there wasn't any schematic to check component by component, all right, signal by signal, so it was a very difficult task to check this thing without a schematic or a board view. Right, so now I'm going to test it now to see what happens. Well, based on the signal that I've checked before, indicate that to me that the laptop is working fine. Alright, so it's now charging. Let's check this side now. Remember before it was turning on and off. So the light here was coming on and then coming off. So let's see. Alright, so it's on, and as you can see, it's now powering up. There we go. Alright, so I'm at the login screen there. Alright, so as you can see there, it's on. Okay, so as you can see, using the oscilloscope to troubleshoot these types of fault, which can help you to repair the most difficult set of faults relating to the problem on the motherboard. So it is a very vital tool to use and critical to learn how to use an oscilloscope to repair these difficult tasks. Alright, and I hope you enjoy, and I hope you learned something, and I'll see if I can fix something for you in another video. Okay, bye.